Thank you for joining me. So you have survived chapter 6. This is going to be your last video for this chapter. Congratulations. Now for this last video, we're going to continue our conversation about inverse relations and go a little bit deeper in describing what makes an inverse a function. How can we tell when the inverse is going to be a function? So first of all, I want to talk about some notation. So if we have f of x, the inverse is called f negative 1 of x. Think of that whole undoing nature of it. So that's going to talk about the inverse. That's how we can note the inverse as f of negative 1 of x. Now, also remember, when you take a relation and you find its inverse, you flip-flop the domain and the range, okay? That's what ends up happening. Remember, you're flipping the x's and y's. So in order for the inverse to be a function, the original function has to be something called one-to-one. Now, that probably sounds a little bit silly, something a little bit over your heads, but what one-to-one means is every y has one and only one x. That should sound familiar to you because that's our definition for a function. A function, every x can only go to a single y. Well, in a one-to-one function, then it also holds true not only that, but also every y can only go to a single x. So to determine if something is a function, okay, remember we talked about the vertical line test. That's how you determine if something is a function. Well, to determine if it's one-to-one, aka to determine if its inverse is a function, it needs to pass the horizontal line test as well. If it passes both, then it is a function and its inverse is a function. Okay, so there's two tests, the vertical and then the horizontal one for the inverse. So let's take a look at how to apply that. Okay, so here, whoops, I have four functions. So here is my y, all right? And remember, to find the inverse, you flip the x's and the y's. Okay, you flip them and now you solve for y. So I'm going to subtract the 9, divide by 2, there's my inverse. So I have my inverse, and now the question today is that inverse a function or not? So to determine if it's a function or not, I'm going to apply the horizontal line test. My original function, okay, if you picture that original function, you don't need a precise graph, but what you need is a sketch. So my sketch of that original function, it's a line with a positive slope. Okay, so you have to be able to visualize graphs here to determine if it's a function or not. Now, horizontal line test. If I draw my horizontal lines, it ever only touches once. So now when I take the inverse of that, that means the inverse is able to pass the vertical line test. So that's what this horizontal line test is for, is because once you flip it, it means that flipped inverse will pass the vertical line test. So what does this mean? Is yes, the inverse is a function because the original passes the horizontal line test. So let's try this again. I have my y there. So exact same steps as yesterday. I'm going to flip the x and the y. And now I'm going to resolve for y. So I have to square both sides. So I get x squared equals y minus 2. Add the 2 over. There is my inverse. And now let's determine, is that inverse a function or not? So again, we need to think of the horizontal line test. So my original function, I know my original function is a radical shifted 2 to the right. Okay? Now think of applying the horizontal line test to this. If I put a horizontal line through it, that means no matter what, it'll only ever touch once. So that means when I flip it, that inverse will pass the vertical line test, meaning yes. The inverse, once again, is a function. So this isn't too terribly difficult. It's just applying one additional step to what we did yesterday. So let's look at this one. So again, there's my y. Flip the x and y. Oh, sorry. Oh, so I need to subtract the 1, divide by 5. And now to undo a cube means taking a cube root. So that is what my inverse is going to look like. Remember, you just do order of operations to get the y by itself once you've flipped them. Now let's determine, is that a function or not? Well, let's take a look at my original function. My original function is a cubic. So it's going to be something like that. Okay? That's how cubics behave. So I take that cubic and I put it through the horizontal line test. And I can see that no matter where I put that horizontal line, it only touches once. So now picture flipping it for the inverse. The inverse will pass the vertical line test. So once again, that means yes, this one is a function. Let's do one more example. So here, I'm going to switch it, and now have my y and x flip. All right, so I need to square root both sides. Remember, when I square root, I need the plus or minus, and then it undoes my square. So I need to remember that. Subtract the 3. So there is my inverse, okay, my inverse function. Or sorry, my inverse relation, I should say. And now I need to determine, is it a function or not? I should be able to picture that original graph, okay? That original function is a parabola shifted to the left 3. This time, when I put a horizontal line through it, note it touches in 2 places. So now picture, when I take the inverse and it ends up flipping, that means it's going to fail the vertical line test. So that means in this case, no. This time it is not going to be a function. That inverse is not a function, it is simply a relation. Okay, so again, those mental images of all these graphs we've talked about, this is going to be critical to your success throughout the this section, okay, and determining whether something is or is not a function. Now, the really neat thing is you can actually use compositions to show if something is a function or not, or to show if something is an inverse or not. So to show you how this works, I'm going to find the inverse of x, or of f of x. So replace that with y. I'm going to flip them. So that means I'm going to have to add the 7 over. Oh, and divide by 2. So my inverse is going to be x plus 7 over 2. And now I can actually use this idea of composites to prove that those are inverses of each other. Because let's watch what happens. So in this one, I'm going to compose the inverse. So I'm going to compose this into the original. Okay, that's going to be my first task. So I'm going to start writing out the original, and then wherever I see the x, I put the inverse. Okay, so now these 2's cancel, so I get x plus 7 minus 7, and I just have an x left. Well, now let's see it the other direction. So here, let's see what happens when I put the original function into the inverse. So now I'm going to put my original function into the inverse, and let's see what happens. So I get 2x minus 7 plus 7 all over 2. Negative 7 plus 7 cancels, so I get 2x over 2, or, oh, I just get x again. And this is something that's actually really interesting, is if you have two inverses and you compose them into each other, both ways, you will always just get x. So the cool thing is this is actually a way to prove that two things are inverses. Okay, compose them into each other both ways, and in both directions, you should get just x back. And that shows you have inverses. So this is kind of nice because it kind of brings together these last two sections we've been working on in this chapter. So I think it's kind of neat. So let's do one more example of this because it's good practice in finding an inverse. So here, let's find this inverse. So I'm going to flip the x and the y. So I'm going to multiply the 4 over, and then I'm going to subtract the 3. So there's my inverse. And now let's use this composite idea to prove that they're inverses. So let's do this direction first, putting the inverse into the original. So I'm going to put this inverse into my original function. So 4x minus 3 plus 3 over 4. Well, negative 3 plus 3, so I get 4x over 4. Oh, that should be a 4, sorry. And that just leaves me with x. Let's do it the other direction. So let's put the original function into the inverse. So I'm going to put this into the inverse. So I get 4, and then that x plus 3 over 4 minus 3. Well, here the 4's cancel. So I get x plus 3 minus 3. Those cancel, and once again I'm left with x. Now this should actually really make sense because inverses completely undo each other. So notice it undoes absolutely everything in the function until you're boiled back down to just x. So again, a cool concept, something I think is worth noting, because if you have extra time on the test, it's a good way to prove to yourself you actually have the inverses. And again, it's just a really good practice to review composites as well. One last idea is when you're solving real world problems, you can't just flip the variables and resolve. You just actually have to undo the equation for the other one. So notice the circle formula. You don't switch the a and the r. You just divide by pi, square root, and of course in real world you wouldn't have a negative area. So there you kind of know that you just kind of plug in the numbers and you undo it. Okay, you don't have to go through all of the work of actually finding the inverse by switching the variables, because in the real world you can't flip-flop variables like that. It wouldn't make sense. So let's do this. The function d equals 4.9t squared represents the distance d in meters an object falls in t seconds due to Earth's gravity. Find the inverse of this function. How long in seconds does it take the cliff diver to reach the water below? And in this image, they're jumping 24 meters. So first I want to find the inverse. Now again, in this instance, when they say find the inverse, they just mean undo it. The inverse in this case is just solving for the opposite variable. So I would divide by the 4.9 and then I would square root. And obviously I don't need to worry about the plus or minus because when we're dealing with time, it makes sense that we're only going to be dealing with positive time. So in real world circumstances, that's what they mean by inverse, okay? They just mean solve it, rearrange it for the other variable. And then if I need to solve it, well, the time would be 24 divided by 4.9. So I can just type that into my calculator and get an answer of about 2.21 seconds is how long it's going to take them to complete that dive. All right, so you've done it. You survived this whole chapter. So for your summary, again, there's a lot of good key points to talk about in this one. I'm not going to tell you what to put because there's so much variety in what you can say of what you found interesting or how you're going to remember what to do. So do make sure to write that summary for me to wrap up this chapter. Make sure you have everything written out in these notes and then come back ready to do your practice work.